Hello, and welcome back to the Mechanochemistry discussions. This seminar series is hosted by the NSF-funded Center for Mechanical Control of Chemistry, or the CMCC. I'm Ashlie Martini. The goal of the seminar series is, as always, to bring the mechanochemistry community together. The seminars stream live on the third Thursday of every month at 11 a.m. Eastern. They are also available to watch anytime on our YouTube channel. We've had an outstanding group of seminar speakers so far, and again, I encourage you to check them out on the YouTube channel. We also have some exciting speakers upcoming in the few months ahead, and we hope that you will join us for all of them. Before we get started, a few thank yous. Dr. James Batiste, the Center's Director, Jennifer Belsick, the Center's Administrative Coordinator, and Katie Floyd and Ryan Kwok, CMCC students, without whom the seminar series would not happen. Quickly, thank you again for joining us for the seminar series. Please do subscribe, follow us here on our YouTube channel, as well as other social media outlets. Finally, a few quick guidelines, reminder that the webinar is being recorded. However, if you have questions, you may email them to us at cmccdiscussions@gmail.com, or you can post them directly into the YouTube channel chat. Either way, they will be propagated to the speaker at the end of the seminar. Last but not least, it's my great pleasure to introduce today's speaker, Professor Seong Kim. Professor Seong H. Kim joined the Faculty of Chemical Engineering at Penn State in 2001 after completing PhD study in chemistry at Northwestern University and conducting postdoctoral research at the University of California, Berkeley. He is currently a distinguished professor of chemical engineering and has courtesy appointments with the Department of Chemistry and the Department of Material Science and Engineering at Penn State. Dr. Kim's research interests lie in surface science and materials characterization. Since he's moved to Penn State, he's established strong research programs in nanotribology and tribochemistry, surface science of silicate glass, and structure property relationships of crystalline biopolymers in biological materials. Dr. Kim has published more than 350 papers, and the H-index of his published work is 70. He recently finished writing a textbook entitled Surface and Interface Analysis, Principles and Applications, which is currently under production through Wiley and will come out in February 2025. It's my pleasure to welcome Professor Kim to the Mechanochemistry discussions.
Hello, hi everyone. This is Seong Kim from Penn State. I really appreciate Ashlie Martini and then CMCC for inviting me to give the chance to describe the chemistry study in the mechanochemistry, and then we call tribochemistry, but tribochemistry is a cousin of the mechanochemistry. So let me entertain you with what we have found recently, and then I will talk about a lot of experiment, but from time to time, the Ashlie Martini group's computation comes in. So if you have any question about the computation, you know whom to ask to. So I guess the mechanochemistry community have a lot of fun in synthesizing some useful chemicals and the materials with the force or stress or collisions or shear or shaking. By education, I'm a physical chemist, so I'm curious about how the mechanical force is inducing or facilitating or catalyzing the synthesis of materials. So that's what I want to talk about today. So I borrowed this picture from the CMCC website, the mechanochemistry, the science of a crush. I would say that the mechanochemistry is a science of rubbing. So when you have the mortar and pestle and mortar, you are not just crushing, you are rubbing, all right? You're grinding. So there's a friction occurs, there's a fracture occurs, there's a wear occurs. At the same time, the chemical reaction takes place. Probably the Sorby was the first person who really mentioned and recognized the potential of the mechanochemistry in 1862. He argued that if the mechanical force can be produced by chemical actions, the converse should be possible. But since then, the effort to understand how mechanical force facilitate chemical reactions and also how to utilize those chemical reactions, activated mechanical force for synthesis of new materials has been studied. And then this is today what we are doing, what we are studying. Whether you utilize those reactions or whether you try to understand the mechanisms. So I'm going to talk about the mechanism side. So as a physical chemist, I'm going to remind you the very basic chemical reaction kinetics. So for example, here I put down I draw the Morse potential of the diatomic covalent bonds. And then so here T, the R naught is the equilibrium bond length distance. And then if you stretch those molecular bonds, then at some point they breaks. And then how much of energy that you have to provide, that's the energy that the D is recorded as a D. So that's chemical reaction, dissociation reaction of the diatomic bonds. So in order to induce that chemical reaction, what we need to do, we usually heat the systems. So by heating, we are providing the thermal energy. Then the chemical reactions gradually start to occur. So how much heat we need to provide? Well, that is governed, dictated by Maxwell-Boltzmann distribution. When we heat the molecules, most of the molecules are in the low energy state, and then the few small fraction has a high enough energy that go over the activation energy. Whereas we increase the system temperature, whole distribution shift to the right, so more and more reaction, the molecules can undergo chemical reaction, so reaction rate goes up. So that gives us this so-called very famous Arrhenius equation or Arrhenius plot that most chemists and physicists, chemical engineers learned in the undergraduate courses. So in order to drive the chemical reactions, we have to go over the mountain. That mountain is called activation energy. And then as we increase the temperature, reaction rate increases. Sometimes that mountain is too tall, too high, so we use the catalyst to lower the mountain, the activation barrier, so more reaction can take place. That's the conventional chemistry, thermally activated chemistry, or catalysis. Now, when we talk about the mechanochemistry, one way to think about the mechanochemistry, how it works, is that the potential energy surface is now modified due to the force applied, externally applied the force. Then the activation barrier is actually decreasing. So this is the diagram that is drawn by Eyring, 1940. Of this diagram is on your website, CMCC website. So it's the same thing, 100 years, we are using same diagram, and then we try to understand the reaction mechanisms. So let's go back to this Arrhenius equation or Arrhenius plot of typical chemical reactions. When the mechanical force or stress is applied, so then activation, our current thinking is that the activation energy barrier is reduced. By how much? The stress that we apply to the system. Then, we can modify this Arrhenius equation. So activation energy is decreased by the mechanical energy applied. So here's a decrease of the activation energy by mechanical energy. So this is called the mechanically assisted thermal activation of the models. And here the mechanical energy can be described by force applied by the length change. So for example, bond length needs to be changed. So then F times delta X, that could be the work that we have done to the system. So that's the mechanical energy applied to the system. That much of the energy is decreased from the thermal activation energy. So the mechanochemical reaction can occur. Another way of thinking is that instead of the force, we can think about the stress or pressure applied to the system. Then we are having the volume terms. So pressure times volume, stress times volume, that gives the energy terms. So this is the equation that I'm going to use today to show how the mechanochemical reaction is activated or facilitated. When we have this kind of equation and then submit the papers, many times reviewer ask, so then the reaction of the that occurs through the mechanochemical pathway. What is the activation energy without applying in the absence of the mechanical stress? Please, please, please do not ask that question because we do not know. The reason is chemical reaction that activated by force is completely different from the chemical reaction that is activated by heat. So there's no way we can experimentally study what is the activation energy under the thermal reaction condition for the reaction that we studied mechanochemically. So that is some our weakness, some limitation that we have to deal with. By the way, this is the end of my lectures. So everything that you need to understand is explained. From now on, I will just show you some few examples, how we studied, how we measured the activation volume, and then how we interpret the activation volume that we measured. So the experiment that we have done is the tribochemistry. So a little different from the ball milling, but much simpler because we know the substrate shape, we know the counter surface shape, spheres. We apply the very specified force or the contact pressure, and then we control the environment. By controlling the environment, we are supplying the reactant to the sliding interface where mechanochemical action occurs through the gas absorption isotherm. So we can study the gas absorption isotherm to find out the amount of the reactant absorbed at the sliding interface. After the sliding, in the case that in the reactions that I'm going to talk about today is some tribofilm formation or tribopolymer formation. So in other words, we deliver the monomeric molecules through the gas phase, molecule adsorbed and then sheared, and then they get polymerized, and then they produce some the products that we can measure. The experimental condition is like this. So in this about the 100 to 400 megapascal contact pressure, this is very light load. So if we have about 3 millimeter diameter ball, if we applied about 100 or 200 grams, then we got that kind of a contact pressure. With that contact pressure, if we do the friction test in dry condition, the friction coefficient goes all over the places. So here I'm showing the 9 different materials. The friction coefficient is the friction force divided by applied load. Sometimes friction coefficient is as high as 1. When we do the exact same experiment in the humid environment, again, friction coefficient is all over the places. When we do that experiment in the pentanol vapor or ethanol vapor or propanol vapor, literally saturated alcohol vapor conditions, then friction coefficient converge to about 0.15. And then when we look at the surface, dry condition, humid condition, we have a huge wear or catastrophic mechanical failure. But in the alcohol vapor condition, all we see is a little bit of the plastic deformation. Very often, we don't even see the plastic deformation. So very clean chemistry. If anything can be produced, anything is produced on the surface, we can measure their quantity by doing the atomic force microscope or the other chemical analysis. So the first example that I'm going to show you here is the comparison between propanol case and then 2-propene-1-ol, so-called allyl alcohols. So what we have done here is we have this stainless steel substrate with a stainless steel ball rubbing in the about 30% of the vapor pressure of those molecules, or about 30% of the saturation vapor pressure. Why we use 30% of the P or PZ? Because we know that it forms a one monolayer of the adsorbate. So that is our reactant. When we do that test in N-pentanol vapor environment, we don't see any wear. Slide track is very clean. When we do the exact same experiment with the exact same material with the exact same load condition, we see some sort of a product is formed. We have done the chemical analysis through the infrared spectroscopy. We see that the polymeric products are produced. via consumption of the double bond. CC allyl alcohol double bond is all gone. And then we even did the XPS, so put the product into the ultra high vacuum conditions, and then we were able to do chemical analysis. The fact that we were able to do chemical analysis in ultra vacuum condition means that this is oligomeric or polymeric products, high molecular weight. So then question is, wait, allyl alcohol, I will show you the text later, but allyl alcohol cannot be polymerized by just this heating. But I polymerized allyl alcohol by just rubbing. How that happened, right? So our Yoda said, may the force be with you. So using that the equation, so the shear mechanically assisted thermal activation model, what we have done here is that we change the contact pressure or shear stress and then measure the yield and then see the correlation between the reaction yield and the contact pressure. And then we plot that in the semi-log plot. So here's semi-log of the reaction yield and then applied pressure. And then as we increase the applied pressure, reaction yield increases from the equation, the kinetic equation. The slope, can be converted to activation volume because we measure the reaction yield as a function of the applied stress at constant temperature. Then we got an activation volume of the 8 cubic angstroms. Now, we measured 8 cubic angstrom. What's the physical meaning of this? Well, we were scratching our head in about 10 years ago. So first of all, the allyl alcohol polymerization cannot occur in the thermally activated conditions. In order to increase the induced polymerization reaction by just applying the static pressure, we have to go ridiculously high pressure, such as the 10 gigapascal, but our condition was only 0.3 gigapascal-ish. So, and also propanol or pentanol, the normal pentanol, normal propanol does not produce any polymers. So we speculated, said there's some sort of the mechanochemical reaction is taking place that we do not know at the time. So that's the time that I called Ashlie Martini. Hey, we have some reaction to study. We don't know how it occurs. So they set up the reactive molecular dynamic simulations. And then, so the system was silicon oxide. And then we put the allyl alcohol. And then we watched the trajectory of all the molecules. And then we found that whenever the reaction occurred, one of the allyl alcohol molecules were chemizobed. And the other very interesting aspect was always the reaction occurs between oxygen and then CC double bond. Typical thermal reaction, chemical polymerization reaction occurs between CC double bond. We never saw that. We see always oxygen and then CC double bond association reaction. Because this is a molecular dynamic simulation, we can look at all the bond lengths and the bond angle distribution. One thing that we noticed that here is that the distance between alcohol hydroxyl group and then CC double bond, the carbon, this end carbon and oxygen, that distance in the static condition is a relatively sharp distribution. But under the sliding and the conditions, the high pressure sliding condition, that distribution becomes very broad. So we kind of get an idea, under the sliding condition, molecules deform out of this equilibrium conformation. Maybe that is causing the chemical reactions of the allyl alcohol that usually do not react under the thermal reaction condition. So first question, the first example. Second example, we looked at the alpha pinene and then pinane and then decane. This is all C10 hydrocarbons. Alpha pinene has a 4-membered ring, so very high, it has very high ring strength. And then CC double bond is a 6-membered ring, so it has also very high ring strength, and then double bond high reactivity. Double bond is hydrogenated, so then we have only 4-membered rings. So there's no double bond, and that decane has no ring strength whatsoever. And then we did the same experiment, rubbing on silicon oxide surface with the silicon oxide ball, and the sliding speed was very low, so there was no temperature increase due to the friction. In that condition, so here what we're plotting here is the y-axis is log of the reaction yield, and the x-axis is the contact stress, so the contact pressure. So based on this equation from the slope, we can calculate the activation volume, and then we measure the friction coefficient and then convert the contact pressure to shear stress, and then we can calculate the activation volume. Again, we measure the activation volume. For the alpha pinene, it looks like only 3% of the molecular volume, and decane is about 10% of the molecular volume. So what is the meaning of the activation volume? Well, we are smart, we think. So we have some the speculations. So in the case of the alpha pinene, using the deformation concept, in the case, because alpha pinene has a very high ring strain or a highly reactive CC double bond, with a little bit of the deformation, it can react very easily. And decane do not have any highly reactive functional group, so it needs a lot of distortion, a lot of torture to go through the activation barrier. Again, that's our hypothesis or speculation. We need computational simulation to prove that it's actually happening. Again, pick up the phone, call the UC Merced, and then talk to Professor Ashlie Martini, and then the Arash Kaya did all the simulation. So here's the alpha pinene on silicon oxide surface. First, it has some surface oxygen group approaches the alpha pinene, and then at between 120 picosecond and 124 picosecond, suddenly chemical bonds are formed between reactant and the surface atoms. So we looked at that time step very carefully. Just before the chemical reaction, just my mouse is a little slow, so let me put here. So just before the chemical reaction occurred at about 124 picosecond, we see that the carbon 1 to carbon 6 bond length is increasing, and then opposite side of the four-membered ring, the bond angle is changing. So we saw that just before the chemical reaction occurs, in this case, chemisorption, deformation of the reactant molecule is happening. So we kind of support our original hypothesis. We now looked at the third system. This is the comparing tribochemical reaction, tribofilm formation yield for cyclohexene, so six-membered ring with a double bond, cyclohexane, six-membered ring with the lowest the ring strain, because of the six-membered ring is the most stable conformation, and then five-membered ring, but the same, the 6 carbon, so methylcyclopentane. Again, we did the exact same experiment. So in this case, we used a stainless steel surface, rubbing with the stainless steel ball. Sliding speed was low enough. There was no frictional heat. So all the reaction is driven by friction or mechanical shear force. So again, this is one example. After slide, I'm sorry, this specific example was the dehydroxylated silica surface. Rub the surface with a stainless steel ball in the presence of the cyclohexene vapor. The cyclohexene vapor partial pressure was kept to about 30% of the saturation vapor pressure to assure that the surface is always covered with one monolayer of the fissure of the cyclohexene, and then we rubbed it with about 1 Newton load. That is about the 300 megapascal the contact pressure. And then after rubbing about 600 cycles, we see a lot of a product is piled up. So these are tribopolymers produced inside the sliding track and then push it to the side and then accumulate it. We had a little bit of the wear. So when we magnify the sliding track by 40 times or 50 times, we can see a little bit of the wear of the substrate. That's the completely different topic. So I'm not going to talk about that part. I'm going to talk about those reaction yield, tribopolymer, the tribofilm production yield. In this case, so we have done cyclohexene. So again, y-axis is a log of the reaction yield, cyclohexene, cyclohexane, methyl cyclopentane, and then we also throw in the molecule, the previously studied molecule alpha-pinene to it, and then measure the as a function of shear stress. And then from the slope, we got an activation volume. We see two categories. So cyclohexene alpha-pinene that has a CC double bond has a very low activation volume. And then the cyclohexane and then cyclopentane that do not have the double bond has relatively large activation volume. So once again, we want to compare with the computation result. So Ashlie Martini's group has done Fakuro has done fantastic the reactive molecular dynamic simulations. And then he found that the cyclohexane, which doesn't have a CC double bond, has to go through the hydrogen elimination reaction first to be chemisorphed. That reaction barrier, the activation barrier was huge, 90 kilocalorie per mole. When we did this, when we used the reflection absorption infrared spectroscopy, we didn't find any hint of the chemisorption. So reactivity were very low because there was no chemisorption, and the activation energy was very high. And then once the chemisorption, the reaction occurs very readily. In the case of the cyclohexene, the first chemisorption step was very facile and that occurs very readily. And again, when we did the vibration spectroscopy, we confirmed that the cyclohexene can be chemisorphed on the stainless steel surface. And then the second, the oligomerization reaction has the activation barrier, about the 40 kilocalorie per mole, a little bit less, but still there's activation barrier. So from this, what we know is a different reactant has a different the activation, mechanically activated process. In the case of the cyclohexane, initial chemisorption step is activated by mechanical force or stress. In the case of a cyclohexene, the chemisorption occurs readily, but the second step is more assisted by the mechanical stress. Now, let's revisit the deformation idea. Physical deformation is a driving force for the reactions, mechanochemical reactions. So in this case, so again, this is a reactive molecular dynamic simulation, the snapshots from the MD simulation. Just before the chemical reaction occur, we saw that there's one of those bonds is deformed, get shorter. So here's the chemisorption occurs in the CC double bond side, but just before the reaction occurs, this opposite side, CC single bond gets shortened. So we did the MD simulation, so-called the Notch elastic band theory, and then we follow the trajectory of the reaction coordinate and the calculated activation system energy. And then we found that when the reacting molecule is physically deformed, then activation barrier is actually decreases. What is interesting here is that originally I thought that transition state energy would be lowered significantly, but what this data shows that no, transition state is not affected much, but the reactant energy state is affected much. And then, of course, from the MD simulation, we found that as the molecule get deformed more, the activation, the energy decreased more. So this confirms that our concept of the molecular deformation or mechanically induced physical deformation out of the equilibrium, the conformation is main driving force for the mechanochemical reactions. Anyway, there's many different types of the mechanochemical reaction or tribochemical reaction or shear-driven or friction-driven chemical reactions were studied. Activation volumes were reported. I think we still do not have a clear concept of what physical meaning of the activation volume is. Here, I'm going to show you the one very new concept. The manuscript was submitted, and this was originally developed by mechanical engineers in the Southwest Jiao Tong University in China, who I have been collaborating for a long time. So here, what we are proposing here is that the activation volume is the effective volume that involved in the reaction. So whatever it could be single molecule, it could be a certain volume where the positions of atoms are moved during the mechanochemical reaction times we define that internal stress. That internal stress is due to metastable conformation or configuration at the transition state. So in initial state the bonding needs to be elongated, or bond angle needs to be changed. So those deformation causes internal stress, and then the comparison to the elastic modulus. So I call this term is the propensity to deform under external stress. So we applied this concept. So here's the Lei Chen and the Yang Wang, very talented mechanical engineer studying chemical reactions. So I try to help them to clean up understand what is the physical meaning of those terms. So here the black line is the potential energy surface in the absence of the applied load, applied stress, pressure. And then when the stress is applied, reactant state is destabilized. And then we assume that the transition state might be stabilized. So it was reduced. So we set out the equation in this way. So this term is here, the sigma T is the internal stress due to metastable configuration. It just comes out of the calculation box. So here what we studied is the silicon oxide surface compressed, and then SiO-Si bond is formed, and then H2O is removed. Transition, and then we found that the transition state based on the by following the trajectory, and then we calculated the absolute energy of the initial state at pressure 0, and then transition state. Compressed a little bit, so the pressure increases, and then we calculate the system energy as well as the internal stress of the transition state. So from this calculation, we think this is the difference in the internal stress at 0 applied load is the internal stress term sigma T. So from that, what we also found here is that because this is the molecular dynamic simulation, we can follow all the atoms movement, and then by looking at those atoms movement, how many atoms or how far the displacement occur. So by following that, we calculated the effective volume. So that's the volume that is affected during the reactions. And then we estimated what is the internal stress term is 3.4 gigapascal. Computer simulation, from the simulation box, elastic modulus is calculated. So then activation volume is estimated about the 50 cubic angstroms. Then now come back to these energy diagrams. So activation energy at the 0 load, at that activation energy at the applied contact pressure. So by plotting this activation energy change as a function of applied pressure from the slope, we can calculate that activation volume. Coincidence, or this explains the activation volume concept? Well, to be tested by the community, by the DFT expert, MD simulation expert. By the way, so that's all I have today. In summary, I will say that the reaction path that are normally inaccessible, does not occur in the thermal activation condition, can be activated through friction, same through ball milling, so collisions is also possible. we hypothesized that the deformation of molecules out of the equilibrium geometry is the main driving force for the mechanochemical reactions. I haven't showed the data, but these mechanochemical reaction is not just sensitive to the structure of the reactant molecules, but also surface chemistry of the solid, as well as the environment of the reactions, whether the mechanochemical reaction takes place, whether there's oxygen present, whether there's water present, whether there's hydrogen present, whether there's other molecules present, they may have the influences. Okay, so before I end my talk, I'm gonna play one video. So the last part of the talk is published in the RSC Mechanochemistry, and then they ask us to make a nice promotional video. So I'm going to play that, and then here you will see the students who did all those work.
Hey everyone, ever wonder what happens when you make two surfaces lie against each other? It's more than just wear and tear. They are occurrence of tribochemical reactions. Tribochemical reactions are the chemical reactions that are driven by heat or by the stresses at the two sliding interface. For example, consider the gears on your bike. When you apply lubricant oil to your bike's gears, it reduces friction between the metal surface. This not only helps the gears move more smoothly, but also minimize wear and tear. This lubrication is a perfect example of tribochemistry at work. The oil forms a protective layer of so-called tribofilm through tribochemical reactions that prevent the direct metal contact. Despite knowing that tribofilm forms, we still do not understand how it is generated. In this study, we explore the reaction mechanism underlying
Please.
chemistry by using a model system. Specifically, the effect of molecular restructure, the presence of unsaturated bond, and molecular size on tribochemical reaction yield were studied. The result from the macroscale tribal test and the atomic insight provided by reactant FFMD simulation suggests that molecules with higher tribochemical reactivity have smaller activation volumes, less negative intercept in a similar plot of reaction yield against stresses, and smaller thermal activation energies. Overall, the study provides valuable insight into the tribochemical reaction mechanism, highlighting the importance of molecular characteristic in determining reactivity. Understanding these factors could help in designing better lubricant and material that optimize tribofilm formation and improve wear resistance. I know this might sound a bit daunting with all the scientific terms, but don't worry. After reading this paper, everything will be crystal clear and way more fun than you expected. So next time you oil your bike or car, you are not just making it run better, you are engaging in a bit of tribochemical magic. Thank you for watching. If you are interested in learning more about this study, please click the link below in the description.
Okay, so here's the link, and then that's all I have today. And thank you, Rob. Thank you very much. Thanks for your attention, and then I'd be happy to entertain any question that you may have.
Thank you for that presentation. We have a few questions from the audience. Let's start with this one. How do you define the elastic modulus of a molecule? How do you determine the elastic modulus of a molecule?
Oh, very good question. I do not know. We have to ask Professor Ashlie Martini. So in the system that I presented in the last, that was a silicon oxide surface. So, it's because it's a solid material, we can define the elastic modulus. We can even simulate, we can even measure. In the case of molecules, very good question. I do not know. I haven't thought about it. This is something that probably we need to study more. Very good question. Thank you.
All right, next question. You mentioned shear and rubbing are the most critical for these types of reactions. How can you explain the dependence of reactions on impact force in ball milling, for example, or reported differences between shear and impact in reactivity?
Another very good question. Impact or the normal force, normal stress versus the shear stress. Always we have these questions because we cannot create the shear stress without having the normal stress. In certain reactions, just normal stress is enough to induce the chemical reactions. But the ones that we studied, we didn't see much chemical reaction by just applying the normal stress. We need to have the shear stress, just friction or rubbing. Another good example is the system demonstrated by the Hugh Spike. They studied the ZDDP, zinc diphosphate, which is used in the current engine lubricant. That works as an anti-wear additive. So when we rub it, it produces some fumes that protects your engine cylinders and then pin from wear. So that the products or the tribofilm, they show that by just applying the normal stress does not occur readily. You need to have the rubbing or friction force. So always we need the friction force. Probably not, just rubbing and if the impact is sufficient. As a matter of fact, the ball milling is a lot of the action is occurring through the impact. But at the same time, I'd like to ask a question. In ball milling condition, is it 100% perfect impact? I'm sure that there's a shear action also involved. So what is the effect of the normal stress and then shear stress? I think this is interesting questions.
All righty, let's do another one. Excuse me. Can you quantify ring strain and correlate that to the susceptibility of a molecule to mechanochemical reaction?
So ring strain can be calculated, and it has been measured in the if we open the organic chemistry textbook, the small molecules, small rings has a higher ring strain. 6-membered ring has the lowest ring strain. As the ring size increases, ring strain increases again. So these have been measured or have been calculated. So we just using the literature value and then comparing with the mechanochemical reactivity. I do not know how to measure it. I have to go back and then open the organic chemistry textbook, but ring strain can be measured or defined.
All righty, let's do just one more here. How can some of these ideas from mechanochemistry be extended? How can some of these ideas from tribochemistry be extended to mechanochemistry for synthesis?
Well, the system that I studied is synthesis, tribofilm, polymerization, oligomerization. How that can be extended to mechanochemistry. Well, you need to have me in the CMCC so I can study those things. I do not know. This is as I said, mechanochemistry or shear-driven tribochemistry are cousins. But as the previous question I asked, he said in one case, impact and the normal stress plays more important role. In the latter case, in other case, the shear stress plays important role. Is there any synergy? Is there any competition? Yeah, probably. Do we really understand? I think I will say that's far from their understanding actually what is happening. We don't even know the tribochemistry mechanism completely. So, that's a very good question. It's something that we need to study more.
Excellent. Thank you again for your presentation.
Okay, thank you for your attention and thank you for having me. If you have any questions, please feel free to send me emails, or you can send you can go to the Penn State Chemical Engineering, then you can find my email address. I'd love to chat with you.
Thank you. Thank you so much, Professor Kim, for that outstanding presentation. And thank you so much for joining us. Just a reminder that all of our outstanding CMCC Mechanochemistry discussion seminar speakers are available to watch anytime on the YouTube channel. We also have some excellent speakers planned for the upcoming months, and we hope that you will join us for all of them. Thank you again.